Okay. So, let's just start the video over because I don't want to chop them up. So for lambda equals 1, 2, 1 is an eigenvector. Okay? So is 200, 100. Okay, so is 666 and 2/3, 333 and 2/3. Any multiple of an eigenvector is also an eigenvector. And the eigenvalue for this eigenvector is 1, which means that when you multiply by the same dimensional matrix to transform the vector, it just goes to itself. Transform vector is identical for any vector along this line. Okay? So it works all the way along this line here forever. All the way along this line, any vector that lies along this line at 45 degrees to the negative x-axis. In the second or fourth quadrant, 45 degrees to the coordinate axes. You have an eigenvector of 0.7. So if you had a vector along here, when you transform it, it would become only 70% as long, which has a whole lot to do with the way the transformed vectors approach this eigenvector in the same dimensional model. So let's just see what the details of that are. So, well, let me just take any old vector in the plane, and let's take this nice straight vector. Okay? This vector can be written as a sum of a vector in this direction and a vector in this direction. Okay? Now this, we haven't talked a lot, maybe not any, about vector addition, but just a quick picture. If this is vector trying to think of good letters to use. I don't use A and B because we're using them in different contexts. This is vector x, and this is vector y. Then this is the vector x plus y. Does that picture kind of make sense? It kind of means like if you start here and go to here, and then from here you go this far in this direction, where you end up with is a vector that goes from here to here. That makes sense? Hopefully. Ponder a little bit if necessary. But that alone should make this picture kind of clear. Okay, so what you have here is you want to express this blue vector as a sum of two vectors, kind of looks like this. One vector along this line and another vector parallel to this one. Okay? Well, the second vector has to be parallel to this one, and it has to go from the tip of a vector on this line to the tip of a vector on this line. Which means that you have to do this along a line here that's parallel to this one. Okay? So this dotted line is supposed to be parallel to that one. I think I maybe have it turned a little wrong, but you get the idea. Okay? Okay, so parallel the eigenvector 1, 1. This dotted line is parallel to the eigenvector 1, 1. And actually, from the angle out, yeah, it's still a little bit, but that's all right. It's a little bit off, but get the idea, okay? And it's not at a right angle to this vector, because this isn't at a right angle to this vector. Okay? So what we do is we just draw the arrow from here to here. Parallel to this eigenvector. And this vector. Okay? So we're going to call this vector we're going to call the 2, 1 vector our V1. And we're going to call the negative 1, 1 vector V2. That's like a triple equal sign. We're defining V2 to be this. It's not totally appropriate, but I did it anyway. Okay? So this vector is a multiple of V1, right? So we're going to call this one C1 V1, and we're going to call this one C2 V2. And we're going to call this our population vector. It might be 700, 300, although not on this scale. 700 be out in the ozone somewhere. Okay? We're going to call this vector P. I'll make a statement that the population vector color code this. Population vector P it's a sum C1 V1 plus C2 V2 of the eigenvectors V1 and V2. So if I multiply this by P, that's a transition, right? That equals this. Because P is C1 V1 plus C2 V2, okay? And that equals this matrix times this, plus this matrix times this because you have a distributive law. You see why I get upset when people come into pre-calculus not knowing that there's a distributive law? See why I emphasize it? There's method behind my madness, okay? It all becomes clear for the rare student who goes a little ways beyond, especially to a challenging course like this one. Okay. You also understand why I really think that the curriculum ought to teach the distributive law a little better and all the laws, because it's a lawful thing. And y'all are smart enough to get this, but people who are just right at the level of somebody who barely understands this course is not going to understand it because of the deficiencies in the curriculum. Okay. And this equals I'm going to leave myself plenty of room. Equals my matrix, which I'm getting awful tired of right now. Hard for you and me to read it. But this is just, it looks like simple algebra, and it is. Once you understand the rules that you can use in manipulating matrices, and they're very simple, very much analogous, except you don't have inverses and stuff like that, okay? To the rules you have for just basic arithmetic. They behave in many ways, just like real numbers behave, in other words. Okay. So, because of the rules, that C1 is just a constant. You could as well multiply it by the matrix and then by V1, which means you could just multiply it by whatever you get when you multiply the matrix by V1, which is the way I would group this. I'm not being careful with my grouping, but now I can say that that's going to be C1 times what? What do you get if you multiply the matrix by V1? Well, there's a lot of stuff here, and you got working memory issues when it goes by fast. Not as bad as mine, but you still have them, everybody does. But what's V1? It's this. And what do you get if you multiply the matrix by this? You get this. That's why we did the whole eigenvalue thing. We had the eigenvalue 1. We ran that through the equations, and we found out that the eigenvector has to be a multiple of 2, 1, and so we just chose 2, 1 as the eigenvector. We like to have nice whole numbers. And the payoff here then is that the matrix times V1 is just V1. And I'll change colors on you. We'll call this V1. Because now it's the V1 you get when you've multiplied it by the matrix. And then it's plus what? C2 times what? Well, what happens when you multiply C2 by V2? What do you get? Well, you have to think back through it. This is a lot to digest. Okay? Been at this for an hour and a quarter. You got to be half brain dead, okay? But it's all here, okay? You just got to sort it out. I'm going to give you a week to sort this out. I'm not going to ask for this. I'll ask for a little bit of this next time just to make sure you're on it.
I can has math.
Huh?
That's what my brain feels like right now is I can has math.
Yeah. Well,
Okay.
And it's a C2, but C2's orange, so I shouldn't have done that. C2 times .7 V2, because V2 has an eigenvalue of 0.7, means when you map it, it goes to the 0.7 multiple of itself. And what does that mean in terms of this? Well, there's C2 V2, and here's C1 V1. Well, this is 0.7 C2 V2. Okay? So that now, after the transition, you're here. 30% closer to this than you were to start with. That explains the 70%, 30% thing. And that you should see that as pretty neat. You should see that there's some steps in here. They're not that hard. You'll get them. But you might not have the whole process in your head so that you can take your matrix and do the same thing with it in your head in 2 minutes. Well, don't expect anybody to do that, although people could. That's pretty good at mental arithmetic. I don't know if I could have managed that. Okay. So this whole picture, this whole eigenvalue picture and everything explains what you saw last week when we did these transitions. And if that doesn't convince you that there's something really powerful going on here, well, the rest of the course will. Okay. Make sense?
I'm gonna take a minute and just write a bunch.